So welcome to tutorial number 3. What we're going to cover today is simulations using ddsim, which is the DD4hep simulation tool that actually uses Geant4 under the hood. So this is going to be the first, tutorial where we're actually going to be doing particle simulations. We're going to split this into two components. First, we're going to start with single particle simulation, so mainly aimed at, detector studies or reconstruction algorithm studies. So we're going to run single particle a single particle simulation, not reconstruction, simulation to the point of hits and detectors with ddsim. And that will give us an opportunity to get a little bit familiar with what this ddsim command does. And then we're going to, in the second part, or probably actually towards the second half of the second part, end with how to run this on Monte Carlo event generator files as input. So that will then be more relevant to the physics working groups. So we're going to start with this command ddsim, and obviously everything here is going to be inside EIC shell, right? If I can type EIC shell correctly, I'm going to go into EIC shell and run everything inside EIC shell. So I mentioned this command ddsim now a number of times. So that's going to be the command we're going to want to use. One of the advantages or one of the things that DD4hep does actually pretty well is whenever there's a command, there's typically a -- help option, which will give us some information about how to run this command, sort of a discoverability, usability feature that is pretty convenient. If you don't know anything about the command, typically -- help will give you a little bit of information, or as in the case of ddsim, a lot of information. So there's a lot of output that is produced here in my terminal. Because I'm zoomed in, it sort of is jumbled a little bit. If you're working with a smaller font size, this will be aligned a little bit better. I guess I can temporarily put this a little bit smaller, but of course now you can't read it, so I'm going to zoom in again. Try to at least. There we go. So ddsim -- help gives us these options that we can pass to ddsim. There's, we can scroll up, and I'm going to scroll up to the let me scroll up to the top of where the first options are. You'll see this in your interface as well, that it puts actually a list of all of the options that you can pass before it lists the entire help with descriptions as well. So you'll see that there's this -h, which is the -- help option. You can pass steering files, compact files, run types, input files, output levels, number of events, and so on and so on. So there's all these different options that can be passed to ddsim. What we're going to do is do a combination of passing options to ddsim on the command line and passing options through these steering files. So steering files are going to be a convenient way to control the simulations. Oftentimes it's more convenient than just passing command line options around, because it allows you to send your steering file to someone else for them to use, or it allows you to keep your command line a little bit shorter. The steering files are going to be just regular Python, so it also allows you in some cases to do some small, algorithmic or programmatic aspects of the development of the simulation in these Python files. So what we're going to do is create a default steering file and look at that file as for example, also a way of passing those options to ddsim. So I'm going to I've run ddsim with -- help here. I'm going to immediately turn this into an exercise for everyone, which is to I'm going to post this in the chat here, which is to look through these available options and then look through these options, and in particular find the option that allows us to specify an output file. We're going to come back to that later, because obviously we're going to want to specify an output file for our simulations at some point. That is not going to be the default file name. And then I also ask you to use this particular option, dump steering file, to print out a default steering file, and then to redirect it into a file. And if you don't know what redirect means, that just means that I will use the is greater than character to direct the output of the steering file that you'll see into the file steering.py. So I'll give you again a couple of minutes to do this, and I'll actually pull up the participants list so I can see if anyone has any questions or is raising their hand. Where is it here? There we go. Okay. And of course, as usual, if you have any questions, feel free to unmute, just ask the question. If you're done and you have directed the output of dump steering file into the steering file, then let me know. And by raising, no, not by raising your hand, by using the thumbs up icon in reaction in Zoom. Okay, I see several are happily following along and are already done with this. I'm going to give it another minute or so for everyone to catch up. So part of the reason why I'm having you direct everything into this steering file is because it's also a convenient way to look through some of the options that are available, since they are explained rather well in the steering file, and since my formatting here doesn't allow me to really go over them as easily as the steering file does. Okay, so when you look through this help output, you should have found as the function or as the option that allows us to specify the output file, one that I briefly highlighted earlier, which is not in this output section, but which is the option, where is it here? Output file. So minus output file, or minus capital letter O, allows us to specify the output file that we want the simulation output to go into. Now to get to the steering file, the option that I should use there is, the option that we should use there is minus dump steering file. And you'll see this produces some output. And I'm going to redirect this into steering.py. Actually, I'm not going to do that in this directory. I'm going to first go to this EIC directory and run that there. So ddsim dump steering file steering.py. No, wait. Redirect into steering.py. That's what I want. So I will now have this file steering.py, which is a Python file. I'm going to open this with less. So I can scroll through this. This is Python code. There's DD4hep simulation that is loaded. There's some units that are loaded. And then we create a DD4hep simulation, object that allows us to interact with the ddsim simulation. What's following are all the options that are also available on the command line. So I can identify here, for example, output file. So whereas there's an option --, output file on the command line, inside the steering file, you can specify sim dot and then output file. Every option here that starts with sim dot is available as --, the same thing in on the command line. So you can combine actually parts that you will specify on the command line, things that change frequently, with components of your simulation that you might not change frequently and that you want to keep constant. All the values it has assigned here are the default values that are used by ddsim. So you'll see here for output file, it actually has by default dummy output.slcio. At this point, we're just gonna ignore that there, and we're gonna run with that default output file, and we're gonna change that later. You'll see there's some global level options where we have sim dot and then just the name of the variable, the name of the option. And then there are some segments where we have sim dot something else dot the option. So these are blocks that combine common or options that are commonly used together. So we have options here about the sensitive detector actions. So that's used to identify where hits are stored versus or which type of detector stores which type of hits. We have a sector here or a block of options that is related to magnetic field settings. So if you want to change how the magnetic field steppers work, you would use these field options. And of course, you specify, if you want to specify these on the command line, you would specify --, field dot delta chord, for example. So there's actions, fields, there's filters. We can associate certain filters to certain detectors, for example, to specify that a particle that is a specific detector is only sensitive to optical photons, or to specify, as is commonly done here, that we want, or in this case, or trackers to have a filter that requires at least a 1 kiloelectron volt energy deposition. This is actually something we're typically in our tracker construction are going to override and set this to a 0 energy deposition, since we also are interested in seeing how low energy hits in the tracker are affecting our reconstruction, for example. So filter as another block of detector or of options. I don't even know what guinea pig is. I've never used it, so I'm going to skip that one. But we've got a particle gun block of options. So all of the options that start with gun will specify single particle initial states and or even multi-particle initial states if we assign a different multiplicity. So so we're going to come back to that one because that's the one that we're going to use. If we scroll down a little bit further, we've got HepMC 3 input files. We've got LCIO options. We've got meta options, which are a little bit more meta. We have output options, which is controlling the output to the screen that is printed. And then let's see, we have some important ones that I want to get to. Here they are. And then we have physics list options, which allow us to specify whether we want FTFP, QGFP, QGSP, high precision physics list, or whatever physics list you want, whether you want to include, for example, optical physics or not. So that would be happening through those physics options. So again, --, physics.list, FTFP BERT is the default. And then finally, at the end, there's also some options to, for example, specify the random seed that's used for the simulation. So if you wanted to do reproducible simulations, you would, for example, always specify the same random seed, or at least know which random seed you're using, so you can reproduce those simulations later. there are some options in this Python file, and I'm going to try to find it, but I don't think it's actually exported here by default. There's some options which take a Python function. So those are going to be options that you can only specify on the in the steering file, that you cannot specify on the command line, because you actually have to give it a Python function for it to work. So one of the things we're doing that way is setting up the optical physics that is used in the Cherenkov detectors. So that is something that will require that we use one of those steering files, or as I'll show you later, that will require that we go a little bit beyond ddsim and use a modified version of ddsim that essentially takes that role of defining those functions. So again, all of those options that are available here, we can also specify on the command line. So what we're actually going to do often is start with a steering file that contains the things we don't want to change frequently, and then pass other options on the command line. The other thing we're going to do is start from a minimal steering file, which doesn't include any of those default values that it has exported with dump steering file, but only includes the things that we actually want to change from the defaults. Why would we not want to store these default values in the steering file? Well, because then we are not able to take advantage of some of the updates that might be happening with ddsim when new versions of DD4hep are being released, where some of the names or some of the functionality of these options might change. The default or the absolute minimum steering file is going to be just these first 3 lines. That's the only thing that's needed in the steering file. I mean, the absolute minimum steering file doesn't even have those first 3 lines, but if you want to do anything that involves just adding a single option, you would at least need those first 3 lines to be able to add a single option. So what we would do if we create a minimal steering file, I'm now going to open this in my editor, or actually I'm just going to create a new minimal.py steering file, and I'm just going to add those first 3 lines, which I conveniently can copy and paste. But you can also edit the steering.py file that you just created and remove all of the bits that are coming after after these initial 3 lines. So I'm going to create this minimal steering file, and I'm going to add things to that as we go along here. So how would we use this steering file? Well, we would write ddsim steering file, and I can pass, for example, this minimal, oops, what am I doing here? Minimal.py, sorry, yes. So this will pass this minimal steering file, which doesn't actually do anything, to ddsim. And of course, it still is complaining about things because I haven't specified any geometry. I've not set the number of events. I've not specified any input files, or not specified a particle gun. So at this point, ddsim doesn't actually know yet what to do. So I'm going to ask you all to similarly, if you haven't already by following along, to create one of those minimal steering files that only contains those 3 header lines, or those top 3 lines, and then also run this through ddsim and see if it's also complaining about what is missing. And then you might start even looking through the help and through the output that it conveniently also prints here. You might start looking at what are the options that we will have to specify to be able to address some of the concerns that ddsim is pointing out. So yes, Oscar is asking, the ddsim command line parameters will override what's specified in the steering file. In in virtually all cases. There are some corner cases. For example, you can define in the Python code, you can add entries to a map in Python, which I think ddsim will not overwrite the map, but it will add to that map, essentially a dictionary. But that becomes more relevant once you get into the details, and it behaves in a way that is sort of what you would expect it to do. So another question from Oscar: where would you go to find a list of existing filters for hits? So there's I don't think there's any command here that just prints out all the available filters. This would require going through the DD4hep documentation and looking at what's available and what's defined as filter. So I don't have a link handy right now that shows what the different filters are that exist. I think realistically, we are probably going to need only one or two types of filters, and that's energy deposition filters and then particle type filters. So those are the only two I think that are really relevant to the type of detectors that we have. But getting a full listing, that's useful, or that's good you pointed out, because that would be a useful feature. Actually, not just for filters, also for some of the other aspects that are specified in the same way. So if you are at the same point here where you've created this minimal steering file, and then I see Devan is already giving me the thumbs up because you know I was going to ask, or you know what I'm going to say. So please also give me a thumbs up if you're already at this point, so we can I can know who's ready with this, and then we can move on. Okay, very good. Thank you. So as ddsim points out, there's some things that are missing here. And let's focus first on this geometry compact file. This geometry compact file that ddsim is asking for, that's the geometry of the experiment we want to simulate. So that's going to be what we talked about last week as the entry point XML file for the EPIC experiment. So how do we provide that? Well, we will have to, as last week, source the opt detector setup script, which we now know has loaded the geometry because the prompt has changed to nightly. So we're going to use the environment variables that this script will have set in our ddsim command. So I'm going to just add this at the end of the steering file. You can also add this to the steering file if you're not planning to change the geometry. Inside the steering file, however, you're not going to be able to use the environment variables as I'm doing here. So you would have to do an additional step of first figuring out what the value of those environment variables is. I'm going to do this now on the command line. So I'm going to specify the compact file. If you go through the help output, you'll see that compact file is how we specify the geometry. So that's the option we should use here. And I'm going to specify detector path, detector config, not .py, .xml. So that's going to pass the geometry to ddsim. We can run ddsim. It's still complaining because I haven't resolved the other two issues that it's having. I still haven't specified the number of events, and I haven't specified the input files or particle gun. So I want to specify here a particle gun to start with. We can worry about input files and HepMC3 files later. So to specify a particle gun, I'm going to scroll up here and go to the top of my help and see where it has information about particle guns. So this is the command I'll want to use. I'll use the DD4hep DDG4 or the DD4hep Geant4 particle gun. There's other things you can do here. You can enable a Geant4 generalized particle source, or you can use a direct Geant4 particle gun. Both of those need a Geant4 macro to be able to run them. So what we're going to do here is we're going to use the gun with enable gun, or -G for short, that allows us to completely configure that gun on the command line. So -G or enable gun to enable the particle gun. So let me go back to my command, and I'm going to pass -G to enable the gun, and I'm going to pass the number of events, which I can specify as -- number of events, or for short, capital N, I'm going to just run 10 events. So this is going to be the first simulation with ddsim in the epic geometry, maybe for some of you the very first simulation. So let's run that. This is going to generate 10 events with a particle gun in the geometry of epic. And you see it's loading the geometry. You'll start seeing some blocks of text that also look similar to those of you who are familiar with it, to what you typically get out of a Geant4 simulation. So it's using Geant4 11 patch level 2. It's multi-threaded. Is what happens to scroll by there. It's initializing physics lists. It's scrolling by with the usual physics list information, including, you know, this block of parameters that everyone's familiar with, because that is usually sitting there for a while before it continues.
Question.
And then it's going to run the 10 events.
Question. Does the program automatically take advantage of all cores possible?
It does not. At this point, when we're using ddsim, it is running in a single-threaded environment. The reason for that is primarily because it needs because we're doing input and output. The output plugins that are being used are not automatically available in multi-core environments. So this is not using multi-core by default. This is a work that is happening in the DD4hep project to actually make that work automatically in a multi-core environment. So this is a little bit of a different, I would say, philosophy between the grid-based environments in high energy physics and sort of how we are approaching our software, where in the grid-based high energy physics environments, it's often one core, one process, or one core per process. Whereas in our future, we much more would like to run indeed multi-core. So that is something that we're actually more interested in than maybe some of the other users of DD4hep. So if we look at what happened here, it has indeed run a simulation. It even gives us a little bit of information about how long it took. It takes about 50 seconds to start up, and then it ran for, well, let's see, where is it here? And total time 50 seconds. Okay, and 27 seconds of that was startup time. This is the startup time is the geometry. This 50 seconds actually includes Geant4 setup time. This may take a little bit longer for those of you who are on CVMFS, where the first time you run the simulation, you're accessing Geant4 data files that you might not have on your system yet, and so CVMFS will actually have to go and get those data files, and some of those may be fairly big, so that may require that it downloads, you know, a few, maybe even 100 megabytes of data files. But at some point, it should continue running and then run these events. Now, if you look at this, and I'm going to scroll up to the first event and then zoom out a little bit so that we can see this maybe a little bit better. Oops, zoom out. There we go. And I should have first changed the zoom and then Yeah. Okay, sorry about that. This doesn't seem to zoom very well. There we go. I think now it should all fit on one line, almost. So for each event, it automatically prints a couple of lines by default. And you can turn this off with some of the output options, but it's actually convenient to have it there for now. You'll see that it simulated a muon with an energy or a momentum of 10 GeV in the direction 0, 0, 1, which is convenient for a tutorial because a muon going in the exact Z direction runs very quickly through our simulation because it doesn't actually see any detectors. So that's probably not what we actually want to simulate. It is not actually doing anything useful. It is just going straight down the beam pipe. So we're going to have to be able to specify, first of all, a different particle type, and then a different direction in which we want to send those particles. Now, if we look at the output options, or the options that ddsim has, I'm going to type this again, ddsim, and we scroll up to the block of gun options. You'll see there's a whole bunch of gun options here, which again, we can specify either here on the command line, or we can specify this inside the steering file. So what we're going to do is we're going to add some of these options first on the command line, and I'm going to ask you to just convert that into adding them to the steering file. So you'll see there's options where we specify the energy, particle type, multiplicity per event, angles in phi and theta, or ranges in phi and theta, ranges in momentum, and then some distribution. We can have an angular distribution that's either uniform, that's uniform in cosine theta, that's uniform in eta, or pseudo rapidity, same thing, or that is distributed according to this FF bar distribution. So DD4hep has a history in fermion colliders where this is a relevant distribution. So we can even change the position of our particle gun, which may be relevant for those of you who are not looking at interactions in the interaction at the interaction point itself. So we're going to want to specify this on our command line. I'm going to add some of these options to my previous command here. So let's see, what are we going to add? We're going to add gun theta min. And I'm going to specify that this should be from 3 degrees to gun theta max to 45 degrees. So I'm going to shoot the particles in the forward end cap between 3 and 45 degrees. Notice how I specify units here. So I can specify a value times a unit, both in angles, and then as you'll see in energy and momentum as well. Because we multiply the unit with its because we multiply the value with its unit with this star character with the asterisk, we have to put this in quotes so that the shell that we're running this in doesn't do strange things with it, like expanding it with files or so. So inside or on the command line, we'll want to have our values enclosed in quotes. Inside the Python script, you can just multiply the value with the unit, and that should just work. As you remember, the header that we copied over, this absolute minimum header for the steering file, that actually includes some of these units and then imports these units. Okay, where am I here? There we go. So I'll want a gun distribution, an angular distribution that goes like cosine theta, or that's uniform in cosine theta. This essentially just means I'm picking points uniformly on a sphere within those theta ranges, as opposed to uniform in actual values of theta. That's mainly relevant for the forward and the backward regions. in the barrel. There's not a whole lot of difference between those distributions. And I'll specify a momentum minimum of 1 GeV and a gun momentum maximum of 10 GeV. Okay, anything else we need to specify? I'm going to specify the particle type, gun, particle, and I'm going to specify a pi plus. The names that we pass here for particles are the names that that Geant4 uses. So so we can pass, you know, mu plus, mu minus, pi plus, pi minus, things like that. If you're getting to, you know, don't ask me what the name is, for example, for a kaon. I don't know if it's k plus or k minus, and whether it's a capital letter K or not, or if it is kaon. Those are things we would have to look up then in the documentation for Geant4. But I know pi plus is going to be a useful one, and then of course E minus or something like that will be useful for most detector studies. Again, I'm putting all of this in quotes to make sure that none of these special characters like pluses, brackets, or stars are interfering with the shell. Again, I can run this, and now it's going to run with pions, pi pluses, in the forward into the forward end cap between those different angles that I've chosen. While it's running, I'm going to point out there's also gun.energy. Try to avoid gun.energy because energy is a rather confusing terminology. Again, some of these tools are developed by high energy physicists where the difference between energy and momentum is not really all that relevant. You know, if you're at 70 eV, no one cares that the proton has a 1 GeV rest mass. But in our case, that actually does often lead to confusion. So when we're talking about ranges here, momentum is much less ambiguous than energy. So I'm not going to specify the energy here, but instead the momentum. So if we now look at the output here, we have, I'm going to look now at this last event here. So we have event 10. It's actually pointing out here that it used a pi plus with a momentum of 8.8 GeV at a 0 vertex, but with a direction that is in the X, Y, and Z, that has the X, Y, and Z components here. And in the Z component, it has a 0.9 fraction of the momentum, which indicates that it is indeed going into the forward direction. You can actually look at all of these other particles too, and you'll see this one is 0.882, 0.722, 847. All of these are indeed going to be in the forward direction. We could be, you know, we could even calculate the angles, and we could plot those angles, and we would see that indeed this is going to be according to the distribution that we've picked. You might be wondering, there's some other values here, this energy, so that's, you know, there's some values that are sometimes shown here and shoot here. This one, for example, where it seems to indicate that this is going perfectly in the Z direction. The way DD4hep sometimes throws particles is it picks a reference direction from which it then calculates that angle theta. This is essentially that reference direction. This is where it actually shoots the particle. So this is the direction that we should look at, not this shoot direction. It's the particle direction that's relevant. So if we wanted to take this now and add the theta min, theta max, gun distribution, gun momentum min, momentum max, and particle type, and add them to our steering file, we would add them as sim.gun.theta min is equal to, or assignment equals 3 times degree, sim.gun.theta max equals 45 degrees, and so on. So we could rerun that entirely without having to specify this on a 3-line long command line, right? So I'm going to ask you to do that, and actually what I'm going to ask you is is to run this now, not in the forward direction, but run this for 10 events in the negative end cap. So again, use a similar angular range. So instead of 3 degrees, use 177 degrees. Instead of 45 degrees, 135 degrees. And use a uniform distribution in eta, just to indicate that we can change this. And I'll also ask you to add a multiplicity of 2. So we'll want 2 particles per event, and I want this to be for an electron. So essentially, double electron events in the negative end cap. So all of those gun options, I'll ask you to add to the steering file. You can run this first on the command line just to make sure that it works on the command line, but then move them into your minimal steering file. Rename that minimal steering file to indicate what it's actually doing, and then run that simulation and verify in the output that you indeed see things go in the negative direction in Z for those electrons, and that you indeed get 2 electrons per event. So this is going to be the first time we actually modify and start to run, actually not even a single particle simulation anymore, but create some output that would be useful in a physics study. Maybe not for 10 events, but. So I'm going to let you work on that a little bit, edit the minimal.py file, and start adding those options.
Maybe again a quick like drop in question here. So for the angular distribution, there seems to be certain distributions that are predefined that we can use, like cos theta, etc. But for the momentum distribution, it just always uses uniform between the two points.
It uses uniform, yeah. So
okay,
if there is a reason why you would want a different distribution, you could certainly consider submitting a bug report or a pull request against DD4hep to have actually change exactly these kind of options in response to our requests in the past. So they're open to that. I could imagine something like a logarithmic distribution would be useful. I don't know if you have any particular ones that you would.
No, I don't even have a use case. I was just wondering, since for one we gave a distribution and the other one we didn't.
Yeah, so it's just using uniform distribution. So in terms of output that you expect here, we're just going to look at these, the output events that it's printing here, and just verifying that it is actually sending 2 electrons instead of pions with the correct energy range into the negative Z direction, because they should now be going primarily into the negative Z direction. So we're not looking at any output files yet. That's going to be the next step. And while everyone is working on this, I'm just going to do the same here. So if you want to follow along with what I'm doing, I'm going to be quiet while I do it. Huh? So if you have gotten to the point where you're able to run this with this new steering file that you created, just give me a thumbs up in the chat.
Didn't you ask us to change the multiplicity as well?
Oh, right. Yes, I didn't do that here. Yes, exactly. So I should, of course, test whether what I have here is actually working. So let me verify that. So who is still working on trying to get this to run?
I have a question, what it means that the multiplicity is 2. What is the picture we have?
So that just, it for each event, it will now generate 2 simultaneous events. So, so for each event, it will generate 2 simultaneous tracks. So in this case, when I've generated these events now, they have not just 1 electron, they have 2 electrons in the same event. Why might that be useful? Well, let's say we're looking into in this case, this is going to be the negative end cap rich detector. We might be interested in seeing how well does our reconstruction do if we have potentially overlapping circles that are generated in the rich there. This would be able to give us a data set that actually allows us to do that. So this is one way of making that work.
Okay, thanks.
Okay.
Can you explain again why the info line saying shoot is always 10 GeV, 10 GeV, but not the actual?
So this is essentially it's setting a reference direction, and I think it's setting a reference direction by picking a particle. So it automatically also gets the default energy value, which is by default set to the momentum maximum, which is why that 10 appears there. It's essentially something about the way how internally that reference frame for the angle is picked. I've not looked into the specific details in a while, but it's kind of confusing that it does print it there, and it may be something that we might want to make clearer in the future. So
another question: for each particle, it now also says in your terminal direction -1 and Z. And
yes,
0,
I
0.
also noticed that just now. I wonder if someone else has figured out why that's the case. I wonder if we need to put degree here. So I can run this again. Does everyone else observe the same thing? That's what I get for doing things on the fly a little bit.
And the question is, should this direction that is given, should this be normalized to unit length?
It should be normalized to unit length, but that still means that it shouldn't go to -1. It should, for the angles that we've chosen here, the minus 135 to I mean 135 to 177. That should still not give us an exact -1 Z component. So I'm a little bit confused why that's the case here. Let me check whether this is true for cosine theta distribution as well. Yeah. But yes, a good observation from whoever it was who observed it. That was not the
Nico.
intention to have them go to exactly -1. So one of the things we'll be able to do is, if this doesn't work with cosine theta distribution, we can simply go back to specifying it on the command line, and that should do the right thing. Yeah. Okay. So apparently, if we have an eta distribution, this doesn't seem to do the right thing. Which is probably a bug we should fix. Okay. Modified instructions is then to use cosine theta instead of eta distribution. In this case, you'll see that they are actually going into minus. Minus is a substantially large Z component in the direction, which means that they're actually going into the negative end cap now, but not entirely along the -C direction.
And the DEG was wrong. It has to be spelled out, degree.
No, they both worked.
They both work. Okay.
Yeah, I think if it had not worked, since it's Python, it would have given us a parse error if we specified something that doesn't work. So I think the DEG, that DEG degrees, they both work. Just like I imagine rad and radian would both work. Although why you would specify rad or radian, I don't know. If degrees is much easier, of course. There is some effort, or there was some effort in the past to try to get some eta max and eta min in there. I don't think that that's as relevant anymore, although with the far forward and the far backward regions, it might be relevant to have some eta ranges there, which is usually how those detectors are specified. So that's something that we can also evaluate, but that's currently not there in ddsim. Okay, so everyone good till this point? Now again. Okay, very good. Thank you. Thumbs up. Perfect. So then we're going to go to the next step, which is to actually look at output that isn't just what we get printed to the screen here, but what is produced in output files. if we look at what's created in this directory that I'm in, you'll see that it has written this, this dummy output.slcio file, which is what we saw in the output option as the default value when we exported a default steering file. That's of course not going to be a very it's not going to be a very useful file name, but it's also not a very useful file format. SLCIO files are not something that we're typically very familiar with. So we're going to avoid writing those SLCIO files. And what we're going to do is specify an output file on the command line. And I'm going to specify this on the command line because I like to often include the number of events that I'm simulating in the file name, so I have some idea of what went in there. So I'm going to specify output file EE. I'm going to use that same name as the steering file. I'm going to add 1E1 events to this. So this is going to be 10 to the 1 events, or 10 events. And I will give this as an extension, which is important because ddsim uses the extension of the output files to determine what file format we want. We're using, as a data model in all of our EIC standard software stack, we're using EDM4hep. So we're going to write EDM4hep.root. This is going to result in EDM4hep data model output inside a root file. So I can now rerun this same simulation, and it will write the events inside. It will write the events to this EDM4hep.root file. I'm just going to copy and paste that command line here in the chat. Hopefully, yes, there we go. So that should allow you to run this as well if you have, of course, that same that same steering file. So once we're done here, we're gonna take a look at that root file to just see what's in there. It will depend a little bit on which system you're on, whether that's going to be easier in a root browser or on your other inside outside the container, or whether that is something that you want to look at on a web interface even. So it's running the same simulation here. It's producing different output because it actually takes a random seed that isn't the same every time we run it. I could specify the random seed to make sure it's the same, but I didn't. And if I look at the files that have been created here, the last file that was created is this EDM4hep.root file. So this is my 2 electron 1 GeV to 10 GeV in the negative end cap for 10 to the first power events. So let's open this file. I'm going to open this in.
Sorry, I have a question. Where did you take the steering file from?
So this is the steering file we created in this previous exercise. Yeah.
Okay.
I can.
The minimal one? No, the one. The one that we
modified a little bit. For reference, I'm going to copy this one into the chat so that everyone can follow along, even if you don't have that steering file from earlier. So let's look at this root file. I'm actually gonna look at this inside the container. I'm going to open this root file in root and then open a T browser. If you're on a Mac and graphical interfaces are more difficult in EIC shell, you might want to open this outside of root, or you could even open it through the root, where is it here? Through the root, JS root website. Oh, there it is, which I'm going to copy here as well. If you don't actually have access to a copy of or an installed version of root right now. Any questions? I hear someone, or no? Okay. So I'm going to take a look at what's inside this root file. Open this with root. And just looking at what's inside the file with .ls, I see I'm inside this T file. There's an events tree, and then there's some metadata trees. The metadata trees I'm going to ignore for now. More advanced use for those. But I'm going to look at the events tree. That's going to be where all of the events are stored. And that's, of course, the ones, the one that we'll be interested in. If you do not see lowercase events, but you see capital letters event, then it likely means that this EDM4hep didn't get parsed correctly. For some reason, I have also a habit of typing EMD4hep. Whenever that happens, I end up with a file that is not in this EDM4hep output file format. And the way you'll notice that is when this is in capital letters and actually contains a completely different data model structure that we're not using. So look for the lowercase events tree in this file. Is also going to be the same tree that is output in the same structure in the same way that gets output by the reconstruction framework. So all of that is consistent between what comes out of the simulation and what goes obviously into the reconstruction, and then what comes out of the reconstruction. So to look at what's in here, I'm going to open a T browser and switch the screen sharing here to my T browser window. Let's do this and share the screen completely now. This one. So now we have my terminal window here and the screen and the T browser on the side. Let's fold this in and let's open everything that's in this events directory or in this events tree. There's many different branches here. You'll see MC particles.
I don't think your T browser is being shown.
Is it not?
I see some kind of text box instead. I don't know if other people see the same.
Okay. Let's try it again. Do you see a T browser now?
Nope. But I don't know if others are having this problem.
Yeah, I also don't see it.
Okay, then we'll do this differently. We're gonna go to, where are we gonna go? We're gonna go to the JS root interface, root cern JS latest, and I will share that one. Okay, now you can hopefully see a web browser with JS root interface.
Yes, we can.
Okay, excellent. So I'm going to load that file, which I stored in this EIC directory. So you can open it in a regular root T browser if that works for you. Apparently, I guess it's maybe related to opening those windows outside of or from inside a Singularity container that Zoom doesn't know how to pick them up. I don't know. So we can look at the branches that are inside this tree, and we've got this MC particles branch. Then we've got event header, something more meta information. We've got ecal end cap p, ecal end cap n, dirk bars. All of these branches have hits at the end. And I can keep scrolling down, and there's more hits and more hits. Some of them are hit contributions. So there's the hits branches, and there's the MC particles branches or branch. So we're going to look at this MC particles branch first. That is what contains the truth information. If I look at which leaves are under this branch, I have what went into the simulation. So in this case, those were the 2 electrons, right? So we expect, if we look at MC particles, the size of MC particles, we expect to see 2 particles per event. But we don't. So this is intended to be the initial state of our simulation, but we also store other truth information in there. So that's why we don't actually see 2 particles here. We see many more particles, including here even up to, what is this, 66 entries, 66 particles that are stored in this MC particles branch for some event. We do see our 10 entries though, which indicates that we are indeed looking at 10 events. So now I'm going to draw a blank. How do I plot things with a selection, with a cut in this interface? I don't know, but that is probably okay. What I'm going to do is I'm going to show you how you can select only the primary events. Those are going to have a special generator status of 1. So we have 10 events here, or actually we have 20 entries that have a generator status of equal to 1, which indicates that these are actually events that came from the generator, from the event generator, and are not events with generator status 0, which did not come from the event generator. So so something we'll often want to do is when analyzing the initial state, and this is probably more relevant not for the single particle or particle gun type simulations, but for HepMC input, when we want to compare the final state of the event generator and the initial state for the detector simulation with what we actually observe, we'll want to look at events with this generator status equal to 1. And you'll see here, there's indeed exactly 20 events there, right? So 20 particles. Those are the 2 times 10 electrons that we expect. We can look and see that they're electrons. If we were to, well, again, we would have to make a cut on generator status and then look at the PDG value, which you can probably do if you have root open on your side, and you would see that there's 20 electrons that are generated with particle data group type 11, and so those are indeed the initial electrons. We can look at their momentum in the z direction. Again, you could select only the ones that are that have generator status equal to 1, which I don't know how to do in this interface here. And you would see that the momentum is all in the negative direction. So that means that they're indeed going into the negative end cap. All of this makes sense. That's what we expect from this simulation. One thing we often do as well, and in particular, which we do in the benchmarks, is we add a specific flag, which I'll copy in the chat, that sets the minimum kinetic energy of particles that are stored in addition to the generator particles. So I will now rerun this this simulation with that flag. Let's see here, with particle minimum kinetic energy of 1 TeV, and that should reduce all the additional particles that are stored in MC particles. This is something that is typically useful if you're interested only in MC particles that are part of the initial state. But it also throws out some additional information that, for example, I think the Rich and some of the particle identification detectors are using to determine what the actual the truth particle state is at the entry point to the Rich, for example, to then be able to use that instead of the generated particle. So so this is something that has its trade-offs. Let's see, this should complete relatively soon then. So I encourage you to take a look at the file that you have, of course, as well, and whether all of this makes sense in the files that you've generated. Okay. 9, and our file is written. So now let me reload that file and look at our MC particles PDG, and you can see that most of the PDGs now are, we've got our 20 electrons here. There's 23 entries here, so this does not get rid of all of the generator status 0 particles, but it gets rid of most of them. If I look at generator status 0, I still have 16 of those. So we do still need that generator status cut to be able to get rid of some of those particles. Okay, that is what's inside this MC particles branch. The
Uh,
other branches, sorry, go ahead,
uh,
yeah.
how do you get particles of 1 TeV? What is our input energy? Or
Oh, we don't get particles of 1 TeV. That's why if we say that the minimum kinetic energy is 1 TeV, that means I don't get written. The reason why there's still some particles in this bin here, for example, is because there are some cases in which we are explicitly writing these particles in ways that override the this minimum kinetic energy. Just like our MC particles or initial generated particles that we throw into the detector, they are always written as well, regardless of what their energy is.
okay. Thanks.
Yeah, I know this is a little bit, you know, it's not a very, it's unfortunate that it is not clear how these events make it in there, and that there's not necessarily an easier way to get rid of them other than using generator status equal to 0 or equal to 1 to suppress all the other ones. So in addition to MC particles, we have all of the hits branches, which is where naturally the hits are stored. These are hits in sensitive detectors, and they are not necessarily equal to what Geant4 calls hits. They're what DD4hep calls hits. There's two types of sensitive detectors which we use. There's tracking detectors and there's colorimeter detectors. In the case of colorimeter detectors, they integrate the Geant4 hits from a single particle while it's stepping through the volumes that are sensitive. In the case of a tracking detector, that doesn't happen at all or in the same way. So that's why there's these two different types which have a slightly different behavior. You'll also see that there's different information stored. So if we look, for example, at the first one here, ecal end cap negative hits, which conveniently is also the one that we just threw a whole bunch of electrons in, we can look at their energy, position, X, Y, Z, and then what energy contributions came this was generated with. I'm going to skip discussion of these contributions because that's a little bit more of an advanced topic, but let's just look at the energy distribution, and you'll see there's energy that goes into this detector. Let's see, unzoom, and we can look at this in a log Y scale. And so we have energy that is deposited by those electrons in the negative end cap. If I were to look at the positive end cap for the ecal, look at the energy there, well, there's nothing there because we didn't throw any particles in that direction. Let me just turn this log off. I guess it is already log off. So indeed, we are, by throwing things in the negative Z direction, we are throwing things in the negative end cap, and it is showing up by having energy in these in the negative end cap, and there's hits that correspond with that energy. There's a whole bunch of hits here with a very small energy as well. So those are just, those are additional hits that that probably are on the outside of some of the clusters, where a reconstruction would combine some of the energy in the smaller bins with some of the higher bins that are that contain most of the energy of the electrons that went there. Okay. So these are two types of colorimeter detector hits. The other type of detectors that we might be interested in is tracker detectors. So let me go find a tracker detector. Let's see, inner tracker, let's see, outer tracker, end cap, negative. So this is going to be a tracker plane on the negative end cap, and it contains different information. In this case, we don't have total energy. We do have energy deposition in that tracker detector. But the interesting part here will be the positions of that tracker, position X and position Y, which, if we were to be able to plot those versus each other, we would be able to see the positions that these correspond with. Someone's going to ask me why there's a spike here at 0, and I don't have an answer to that. Why would there be a spike at 0? I have no idea. But so this gives us positions in those tracker detectors. One of the things that is common between both of those detectors is this cell ID. What DD4hep does with sensitive detectors is it assigns a segmentation to them, which we talked a little bit about in the previous discussion. So instead of implementing each pixel as its independent sensitive detector, we add segmentation to a single sensitive detector and assign a cell ID to each pixel. Apparently, if I plot this, it doesn't want to plot in this interface for the trackers. Okay, for the colorimeters, it plots the cell ID. It's essentially a bit pattern, which means that there's not really any logic to which values, or there's not any visible logic to a histogram when we plot just the values of cell ID. So that's what is stored inside that inside these trees. So the MC particles branch and the hits branches are what come out of the simulation. So I'm gonna copy and paste this exercise now. So I'll ask you to do something very similar, which is to just open the same file that you created, or also open it in JSRoot, like I just did. And then plot the z component of the momentum for those particles, but only for the generated particles. So for generator stat is equal to 1. So verify that is consistent, and then plot the deposited energy of hits in the ecal, just like we did, and compare again as we did the positive and the negative end caps to really verify that there's more hits in the negative end cap than in the positive end cap. And when you're done with all of those steps, whether you use root inside the container or outside the container, or whether you use this JSRoot website, just put it a thumbs up in the reactions. So this is actually going to be the start of the break then. So we're going to take again a 5-minute break or so. allow everyone to stretch their legs, and then we're going to pick up after the break with running HepMC input files through the simulation. So a slightly more interest to the physics working groups. So I'm going to actually stop the recording and allow everyone to take a break here. So we're going to now go into simulation of actual physics events. So we're going to start from a HepMC 3 input file, and we're going to use for that the HepMC 3 input file that was generated by Pythia 8. For these input files, which are typically large and there's many events in them, we store those on S3. So one of the things we're going to need to do is access these files through S3. Fortunately, inside the container, we have all of the tools that we need to access those files on S3, including this command MC, which is the Minio client to be able to access them. So if I type MC, it's going to give me a little bit of help on how to use the Minio client to access those files on the S3 storage at BNL. Now I do have to tell MC where those files are located. So the first thing we're going to do, and to some extent, some of you may not actually need to do that, is I'm going to add a new host S3 that will be, or a new, I guess what this does is it adds a configuration called S3 that will point to this particular URL, and it will use a username and a password that I'm going to specify here as environment variables, just so it works, but I'm not going to put in the chat or so. But some of you may be familiar with these already. So these are EIC S3 read, all lowercase except for the S. And that's going to be both the username or the access key and the secret key, which is equivalent to the password. So I'm just going to say these one more time. So EIC S3 read, one word, all lowercase except for the S capitalized. So that gives you read-only access to those files. Say again?
No underscores or anything?
No underscores, no, just, and I'm not putting them in the chat. I'm not putting them in any digital form so that they don't get, automatically put on the internet. I already feel bad enough putting them on a recording of of a meeting. But anyway, so that's going to set up the configuration S3, and it's going to say added S3 successfully, and you'll be able to do something like MC config host list, which will then print to the screen, in your case, whether it's been successfully added. I'm not going to do that either because it actually happily prints that secret access key and the secret password, which are not all that secret because I just told them. So after I've done this, I can use S3 as an alias for any kind of directories, for any kind of operations that I want to do with this MC command. And in particular, I'm just going to do a listing here, ls with MC, of the directory, in a sense, EIC test epic tutorials under the location S3. If I run this, it should pop up one single file, one single lonely Pythia 8 neutral current DIS file of 10 by 100 GeV beam energies with a minimum Q score of 1, with all beam effects and crossing angle of -0.025 and high divergence HepMC file. So that's the one file it should pop up when you run MC ls S3 EIC test epic tutorials. File specifically there for these tutorials. Now this is a large file. It's 5.6 gigabytes. So we're not going to want to download this entire file. And certainly for the purpose of this tutorial, we're not going to want to run a simulation over this entire file. What we're going to do is just take a look at the first few thousand lines. Actually, we're not even going to take a look at the first few thousand lines. We're just going to take a look at the first maybe 100 lines, and then look at and then download somewhat more of it. So I'm going to look with this head command. I'm going to specify, let's say, 100 lines of this file, S3 EIC test epic, and then I want that particular file. So that's going to give me just the content of the first 100 lines of that file. You'll see, and let me copy and paste that command in the chat here. Nope, there we go. So you'll see this is a HepMC version 3 file. Those of you who are familiar with HepMC files might recognize the structure here. So this is event number 0, and it consists of a number of particles and vertices. And there's event number 1, more particles and vertices, event number 2, and then it gets cut off because I reached my 100 lines. If we want to just, if we wanted to copy that entire file, all 5.6 gigabytes to our local computer, we could do that, but I'm not going to do that here. I'm just going to take, instead of the first 100 lines, I'm going to take the first 20,000 lines and redirect that into a file that I'm going to use for this tutorial. So just redirect that into this HepMC file. Again, I'm going to copy and paste this command in the chat for you to run as well. So this should just take those 200,000 or those 20,000 lines and put them in that file. If I look at the word count and the number of lines in that file, it should give me exactly 20,000. So that now I have a HepMC file with 20,000 lines worth of Pythia 8 simulations. And we're going to use that one to start our simulations of those events in our detector. So how are we going to run this? Well, we're going to run this again with ddsim, right? If I go back to my previous commands where I used ddsim, I had specified the steering file. Now I don't need the steering file anymore because the thing that was included in the steering file was how to use the particle gun. So I don't need to specify this particle gun. I do need to specify my command line, my compact file, my geometry. I don't need to use a particle gun. I'm going to stick to 10 events for now. I'm going to change the output file here. So that's, I'm going to rename this to, or I'm going to use Pythia 8 ncdis 10 by 100 1e1.ddm4hep.root. And I'm going to keep this particle minimal kinetic energy there. I'm going to pass the input files option. And it's called input files plural because I can actually specify multiple files there. In this case, we're just going to just specify one file, and it's going to be that HepMC file. So this is going to run these HepMC events through the detector configuration. Is going to do that for 10 events and write it out to that ddm4hep.root file. So this should work. Famous last words. This should work. And you'll see it's still going to print for each event those same lines, but they're now going to be not particle gun lines. It's going to print the lines that correspond to each of those events from HepMC, or from the HepMC file.
Unless you're very lucky with the 20,000, you're going to have the last HepMC event broken. Is it going to choke on that?
Not if I limit myself to 10 events as I've done here.
So, yeah, that'll do it, of course.
Yes. So you're right. There is a risk that we cut off our events at the end, and it is very likely that that will happen. And I'll come back to that in a second here. After these 10 events are done, one of the things you'll notice, these are Pythia events. They typically have a fairly large number of events in the final state, typically with a higher energy than what we've done in single particle simulations. So it actually takes a little bit longer. As you can see here, it's talking about 33 generator particles, 28 generator, 15 generator particles. The number of lines in the HepMC file for some of these is typically on the order of about 120 on average. So if you wanted to do the math, there's about 200 events that we've downloaded, where again, as Kolja pointed out, the last one is going to be chopped off. So we can see from the output here that we are simulating things that are not single events. They're also given different primary vertices, which is what comes from the crabbing and the smearing that is added to this Pythia event file. We'll have generated an output file here. So this is our Detector.root output file. That will contain all of those events and all of the hits generated by these events. I do want to add one thing to Kolja's comment. We do have a little utility, sanitize HepMC3, which is intended, maybe not exactly, but is intended in part also to deal with ill-formed HepMC3 files. So if you have a HepMC3 file that is chopped off at the end, you can use the sanitize HepMC utility to clean it up and add a proper ending to it. It's just going to throw away that last partial event so that no one chokes on it. But I'm not going to talk more about this particular tool. Okay, so we could open this file again. We could open this in our same root T browser. We could look at the hits that are left in this detector, in the detectors. We could look at the MC particle branch, and we're actually going to be able to see a lot more different particle data group values there, because of course these are going to be different particles. So actually, let's do exactly that. Let's see. There we go. End the sharing here, and I'll open my root T browser window from before. And I'll open a different file, which is now this Pythia 8 neutral current DIS 10 by 10 with 10 events in Detector.hep root format. So that's this file here. So the events branch again contains the same structure, MC particles and then all the hits branches. In MC particles, you can look at the PDG codes, and they're all over the place, including 2112, 2212 for neutrons and protons, and neutrons, some order, no, neutrons and protons. We've got some antiparticles here, probably negative pions at minus 211. So we get stuff in here that we would otherwise not get in single particle final states. If we look at the generator status, we'll also see different numbers here. So whereas previously we had zeros and ones, where ones are the things that get thrown in the event and into the detector, now we have particles that have higher codes for generator status, which corresponds to the internals of the event generator, in this case Pythia 8. So some of these codes will correspond to, some diquark internal to the event vertex. Some of these where or value for generator status is 2 corresponds to, for example, a row that has already decayed into 2 photons. Event generator status 4 will correspond to the incoming beam particles. And as you can see, there's exactly 20 incoming beam particles because the HepMC input file for 10 events contained, for each event, 2 incoming beam particles, the electron and the proton. So all of that is accessible. For example, we could, from this incoming beam particles, figure out exactly what energy and angle the proton and electron came from, even after the beam effects were applied. So there's some additional information in here which would not even be accessible in the experiment. But only the events that have generator status 1, or only the particles that have generator status 1 would be the ones that were thrown into the detector and that were processed by Geant4 to into hits and a final state. So now, of course, we have this. We can't really do a lot with our hits. I mean, we could look again at our energy depositions in the ecal end cap. So now on the positive side, we also have energy deposition in the ecal end cap negative. Where's ecal end cap negative? Ecal end cap negative. We have also energies. So we also have hits that are being that are caused by some of the particles going there. Now, of course, the next step would be to use, at least in this case, would be to use the event reconstruction. What would this be useful for? Again, if you have a way to make correlation plots, it might be useful to look at the D-rich and plot X versus Y positions. You might actually start to see some Cherenkov rings, except you won't. And this is going to be the last part of the tutorial today, and that's going to be focused on npsim, which is different from ddsim in a couple of very specific ways. Okay, before we move to that, any questions about how you would run a HepMC3 input file?
Can you repeat S3 access key and secret code?
Oh, EIC S3 read, and so it's everything lowercase except the S in S3, and it's all one word. And that's both the username and the password.
Thank you.
Okay. Maybe we'll edit that out of the recording. I don't know. Let someone else worry about that. Okay, good. So let's go back to the terminal now. Stop share and share again in a terminal window. So we've talked about ddsim, and ddsim minus help gives a lot of output. And then we have npsim, which you'll see is also a command that you can run. And npsim minus help produces the exact same output as ddsim. Now, why do we have npsim? And there's some of you who have been using npsim, and it's perfectly valid to use npsim or ddsim. There's an important reason why we use npsim, and to do that, I'm going to open the internals of npsim to show you what the differences are. So npsim, if I figure out where npsim is located, npsim, it's actually located in the container under that location, but it's really just calling the npsim.py Python script that's right there. And let me just point out what npsim does that regular ddsim doesn't. That's the parts that are included here. So it's really just like in the steering file, it's creating this DD4hep simulation object and then setting things by default on this sim object. What is it setting? It's telling all the trackers to run by default without an energy cutoff. Remember, in the case of ddsim, it's using a 1 kilo electron volt energy cutoff. it's telling, it's adding a new particle filter. So this shows how to create new particle filters, which in this case we call optical photon selector, and we require that the particle is an optical photon. And then we assign that particle filter to the d-rich. That's two things it's doing. So modification of the trackers, modification of the d-rich. It's, let's see, what's remember at the beginning, I talked about one thing that you can only do in the steering file, that is options that require a Python function. So it's actually setting up one of those options here. And what it does is it enables Cherenkov physics and optical photon physics for everything that's run with npsim. So if you want optical photon propagation or Cherenkov light generation, you'll have to run with npsim. And it maps one special sensitive detector action to the rich to allow it to absorb those optical photons. So this is the sum total of all the changes that are in npsim that are not in ddsim. One of which, this one, you would not be able to specify on the command line, and the others are essentially, cumbersome to always carry around on the command line. So unless you're interested, well, I'm not going to say no one is interested in the d-rich, but unless you're really focused on using the d-rich and you rely on that, you can use ddsim. It will go faster because it doesn't need to run the optical photon simulations, but otherwise npsim will give you the optical photon simulations as well. Running it is exactly the same as ddsim, so it's just a matter of replacing dd with np. I can pass this along. You can pass the same steering files to npsim that you use for ddsim, and it should all just work fine. So this will run a little bit more slowly now with npsim because it is going to run DIS events through the d-rich, which are going to cause optical photons, and those, we're probably looking at from a few to several hundreds or even thousands of photons that are being tracked, of which, of course, not necessarily all of them reach the detectors, but those all have to be kept track of by Geant4, and that slows things down a bit. So that's the one thing I wanted to end with is, and I would encourage you now to all, use it as an exercise too, to run npsim, and just, I guess, verify that indeed this works as well and gives us the same, a similar output file. One of the things you would be able to do even is compare the actual time it takes after it prints this out, but you can see this already while I'm running this here. It's about a factor, maybe 2 or 3 slower. Okay, and I think that's about everything I wanted to talk about this time. So this is gonna be the end of the tutorial, and I am open for any questions. I apologize, the last bit was kind of, not as much of an activity, but more of an explaining part.
I do have a question, but it is only semi-related. Is there a way to steer this whole setup from C++? So write C++ and link to DD4hep libraries and use it that way?
I imagine so. All of what is written in DD4hep is C++, so right. you could do that, yeah. Is there a specific use case you have in mind?
I have specific user cases in mind, more or less. There's not everybody loves Python as much as they love C++ and vice versa.
Fair enough.
I mean, one case in point is interfacing this with East, for example, which is currently 100% C++.
Mm-hmm.
But yeah, okay, I'll hunt around for it myself.
Yeah, I mean,
Thank you
I've
very
not.
much for this. This has been a lot of work again. You are a machine of tutorials.
Yeah, I produce tutorials Gatling gun style. So yeah, unfortunately, I don't have any existing experience or no experience with steering DD4hep simulations from C++. So any other questions? Does everyone feel like they would be able to run a simulation now, or do you feel like you're able to run the simulations that you're interested in, at least, whether they're for physics topics or for detector studies? And if not, is there something I can help with? Okay, well, if there are no questions, I'm going to stop the recording here, and maybe there's still some chats after that.